So in yesterday's class we learned how to systematically write down the equations for any circuit, okay, in matrix form. So let's quickly review that. Let me see, I don't have a recording of this circuit. I'll write out the circuit, you can tell me if this is the same circuit we did yesterday, okay? Is this right? Okay. So this we called R11, R22, R33, R12, R23. So this was node 1, node 2, node 3 and node 4, right? So this circuit has 4 nodes. As always, if you want to know the relationships, there are only 3 independent nodes for which you need to find out the voltages, right? What we are studying here is nodal analysis, where you write down the KCL equations at every node, okay? But the variables that we have chosen will be the voltage of every node, okay? We will use the KCL, okay? And there, as we saw yesterday, there are some other, obviously to solve these equations you need to use all of them, and as we saw yesterday, some of them were implicit. So let us quickly write down the equation in matrix form. Okay, so what is the first term? What was the form we want to write this in? We want a conductance matrix, okay, times a voltage vector, okay, which is the variable vector, is equal to a current vector, which is the set of independent current sources, right? So the circuit we are looking at consists of resistors and independent current sources so far. That is really the easiest case, okay? And if you decide to write down the conductance matrix, you can actually, especially for these kinds of simple circuits, you can directly write down the conductance matrix, because we have seen what we have written down the equations in yesterday's class, okay? All 3 equations at N1, N2, N3. N4 is the reference node. So I'll represent it here. N4 is the reference node. Okay. So what is the first term in the conductance matrix? So I'll write down the matrix form like this. So first of all, the variables are V1, V2 and V3. Okay. So in other words, these are the voltages. The voltages of nodes 1, 2 and 3 with respect to the reference node, which is N4, are V1, V2, V3. So the variable vector would be V1, V2, V3. Okay. What did we have on the right hand side? That is the source vector. So this would contain the sum of all independent currents entering the corresponding node. In this case, you only have one current, which is IA entering N1. Okay, so that is IA. Node 2 has no independent current sources, and node 3 has IB entering the node. Okay. What about the conductance matrix? We learned how to write this also. So first of all, each row will correspond to the equation, the KCL equation for that particular node. Okay, so this will correspond to node 1. So I'll have something at node 2 and node 3. Okay, and the terms are also easy to write down. First of all, the diagonal terms. What are the diagonal terms in this conductance matrix? Would be the sum of all the conductances connected to that particular node. Okay. So in this particular case, I have G11 plus G12, right? I only have 2 conductances connected to that node. What about the second diagonal element? I have G12 plus G22 plus G23, and for the last one I have G23 plus G33. Okay, so it's pretty straightforward to write down the conductance, the diagonal elements of the conductance matrix. What about the off diagonal elements? We said the off diagonal elements, okay, can also be written down by figuring out what the equation would look like. We actually wrote down the equations, built the matrix, and then found out the pattern. Okay, and then you go back and get some intuition on as to how the pattern came about. Okay, what is the row 1 column 2 term? What does that correspond to? It corresponds to the term which is going to multiply V2, okay, for the KCL at node 1. Okay, so that should depend on the resistance or the conductance connected between nodes 1 and 2. Okay, but in this case, if you had written the equation for KCL for all currents leaving the node, the current direction of choice would have been in this direction. Okay, that current shown in blue would have been V1 minus V2 by R12, or G12 minus G12 times V1 minus V2, right? Sorry, G12 times V1 minus V2. So in other words, this term would have a minus G12 element. Okay, this term in the matrix, in the conductance matrix, would be minus G12. Okay, what about the third column in row 1? That corresponds to, that should depend on the conductance connecting node 1 and node 3. In this particular circuit, the simple circuit we have taken, there is nothing connecting those, so this should be 0. Okay, and as we saw, this matrix, conductance matrix, is also going to be symmetric. Okay, because of the way we write the KCL equations. So you will have minus G12 here, you will have 0 here. Okay, what else? What about row 2 column 3? That would be minus G23. Okay, so you can actually look at the circuit and figure out what the conductance matrix would look like. And so in simple matrix form, we are writing it in this form. So the product of the conductance matrix times the voltage vector would be the current vector. The current vector is the represents all the independent current sources. The voltage vector represents the variables that we want to solve for. So you can go ahead and solve for the voltage vector by inverting the G matrix and so on, right? You already know how to do that. I don't want to, we're not going to spend time in class doing this, right? If I give you a 3 by 3 matrix, it's expected that you know how to invert the matrix and solve it. How would you solve it? What kind of methods do you know to invert matrices? Anybody? Okay, so I guess you'll have to brush that up, right? You should learn, I guess there are several ways which you probably learned. You should, has anybody heard of Cramer's rule? Okay. Any other methods to invert matrices? Any? Do you know what an adjoint of a matrix is? You know all these techniques, right? I can assume that you know all of these. In any case, even if I don't assume that, I can't spend time in this class, right? You learn this in mathematics so that you can use it in this course. Okay. Fine. So we will assume that you can go ahead and solve this and figure it out. Now, of course, we have taken the case of a very simple circuit, right, which has really 3 nodes, right? 4 nodes, 3 independent nodes, and so on, and only a few elements here, right? But the real power of this is that matrix inversion, or solving these kinds of equations can be computerized, right? If I am building, if you take an integrated circuit, for example, today, it will have, probably, tens of thousands of transistors, if not millions of transistors. You can actually write down this in matrix form, of elements, right? I should say transistors, of elements, okay? You can write down, these equations for all of those. Let's say I had thousands of current sources and resistors. You can write down these equations in matrix form you can use a computer to invert this, right? And then get the solution. We know how to do inversion for 2 by 2 and 3 by 3. Beyond that, it's probably out of our, it's not, it will take a long time for us to do it by hand. Okay? But we have the option of using simulation tools to help with this. Okay, any questions on this this particular technique for so far for independent current sources and resistors? Okay. We also saw what will happen if you start adding other current sources. For example, if I had added a current source like this, okay, I'll call that IC. What will happen to this equation? So this is an independent current source, okay. So I don't expect the conductance matrix or the voltage matrix to change. What should change is the source vector on the right hand side, okay. So IA represents, what does IA represent? Sum of all currents, this term, okay, column row 1, right, should represent the sum of all currents, all independent currents, okay, entering that node, right, because this is on the other right hand side of the equation. In the original case that was just IA, now it is IA minus IC. Okay. What about 2 and 3? Row 2 and row 3, do they change? No, they don't. Okay. If I had a current source like this, what would happen? So I'll call that ID. What would happen? Right. Okay. So you will have IA minus IC minus ID. Okay. And the second row term would now have a plus ID because you have a current entering this. Right. Now you see it's pretty straightforward to do this for any circuit containing these two kinds of elements, resistors and independent current sources. Okay. Now, after yesterday's class, some of you came up to me and asked me, what will happen if you have voltage sources, right? So that's what we're going to see today. Okay. Let's see if I can start from the same. Yeah. So I've just modified the original circuit slightly to include a voltage source. I'll call it Vx. So this is still N1, N2, N3, N4 is still the reference node. So what would you do in this case? Can somebody suggest a way to solve this? So let us say you start writing KCL at N1, N2, N3, right? Can you write down KCL at N1, N2, N3? Okay. So let us say you try to write it at N1. What will that look like? Same thing, right? Sum of all currents leaving the node is 0. So we can again define the voltages as V1, V2 and V3. Okay. So remember, in the original case, the use of KVL and the use of element relationships in nodal analysis is implicit, right? You write down KCL explicitly, but implicitly you are already assuming some relationship inside the element as well as writing KVL. Okay. What do you do for this guy? KCL at node 1, what does that give you? sum of all currents leaving the node. So I have G11 times V1. Okay. What else? Huh? From N1 to N2, what do you have? What current is that? Do you know that current? Okay, so you don't know that current, right? In fact, this is a voltage source. That current could be anything, right? That's the definition of an ideal voltage source. Okay, is that it will maintain a voltage difference irrespective of what current flows through this. So what will we do? So that is an unknown variable. So let me call that Ix. Okay. Plus Ix equals Ia. Okay. So actually let me rewrite this on the next page because it will be easier. So this is KCL at node 1. At N2, what do I have? What do I have at N2? Current, sum of all currents leaving the node. Okay, so minus Ix. Okay, I'll write it slightly differently. So G22 times V2 plus so in fact G22 plus G23 times V2 minus G23 V3 minus Ix equals 0. Correct? Is that right? So the equation for at N2 would remain there. Similar to the earlier case, I have a current V2 by R22 flowing through G22 times V2 flowing through R22. Okay, and I have G23 times V2 minus V3 flowing out. Okay, so I have combined those two terms into this G22 plus G23 times V2. Okay, so I have combined the V2 terms. There is one small step I have kind of jumped here. I'm assuming you have all seen this. I mean, you're all able to see this. Then of course the V3 terms, I'm writing it separately. Of course I have a current Ix coming from node 1. Okay, so that's minus Ix leaving the node and should be equal to the sum of independent current sources entering that node, that is 0. Okay, very good. What do you do next? What do you do about this equation? Now you can't write down the conductance and the matrix G times V is I is not so straightforward anymore, right? In fact, you have an extra variable now, right? Ix. How do you propose we tackle this issue? Write V2 as V1 plus Vx Any ideas how you would propose to solve this problem? So first of all, there are a couple of things to note. Okay, so the minute you have this independent voltage sources coming into the circuit, things are not going to be as simple as the previous case, where you had a G vector times the voltage vector, G matrix times the voltage vector is the current vector. Okay, things are not going to be so simple. So because of this extra variable Ix that you do not want, right? We started off assuming that we are going to calculate all the voltages, right? V1, V2, V3. So let us first do that. If you solve for V1, V2, V3, can you solve for Ix? Of course you can, because directly KCL at node 1 gives you Ix, right? It is once you know the voltage variables, you can go and back calculate currents if you want to. Okay, so let us still try to concentrate on solving for the voltage variables. So we want to eliminate this Ix. So what I'm going to do is I'm going to add these two equations Okay. If I add these two equations, what does it give me? G11 times V1 plus G22 plus G23 times V2 minus G23 times V3 is IA. Okay. So in other words, I have actually eliminated this variable Ix. Okay. So in other words, what I am actually doing is I am actually defining I'm going to define what is called a super node. Okay, I'm going to combine nodes 1 and 2. Remember what we said earlier. Okay, you can write KCL even for an agglomeration of nodes if you want, or for a surface, or any particular structure. Okay, suppose I had originally combined nodes 1 and 2, okay, and written KCL for this super node. Okay, I'll call this a super node. Okay, if I had written KCL for the super node, what would that have looked like? What would that have looked like? You would have got V1 times G11, okay, V2 times G22, okay, plus V2 times G23 minus V3 times G23 is equal to sum of all independent currents entering the super node, which is just IA. Okay, you would have ended up with this equation. Okay, you would have ended up with this equation if you had written KCL for the super node. Everything clear so far? Okay. So now we actually have an equation representing, having only the conductances, the voltages, voltage variables V1, V2, V3 and independent current source IA. But we actually have a problem. What is that problem? What is the problem? We lost an equation, right? We originally, when we wrote KCL at node 1 and node 2, we had two equations, but now we have merged them and we only have one equation, right? So we need one more. So when we merge two nodes into a super node, we are actually losing an equation. So we need to make up that equation. And what is that equation? Somebody mentioned just a little while ago. You know that the independent voltage source constrains the voltage difference between these two terminals, okay, to be exactly equal to something. So we'll write down that relationship. Okay. So V2 minus V1. So I'll write it as minus V1 plus V2 is Vx. Okay. So this gives you the extra equation in terms of the voltage variables V1 and V2 and V3 if need be. Okay. To solve for the voltage variables. Is that clear? Now all you have to do, if you want to build the matrix, okay, you would build the super node. Okay, for all the original nodes you would write it, the conductance matrix, the voltage variables, everything as such, okay, and independent current sources. You will also have one extra equation which will go into the matrix, which will not have conductance values. You can see in this case it only has some constants, right? In this case it's minus 1 and plus 1. So you would actually have a row in the matrix, right, which would look like minus 1, 1, 0, okay, times the voltage vector V1, V2, V3. I hope everybody sees this. And the right hand side would not only have independent current sources, but also these independent voltage sources. Okay. So you can still write this in matrix form. Okay. So I'll just write it like this: G slash something, okay, times the voltage vector would be equal to a vector consisting of independent current sources and independent voltage sources. Obviously, this matrix, this G slash, the constant matrix is no longer going to be symmetric, right? Because you now have a different structure to it, right? But you can still go ahead and invert it and find out what V1, V2, V3 are. You can find out Ix later, right? From any one of those nodal equations. Any questions about the supernode, construction of the supernode, how you would set up the equations? Okay. I'm going to take the same network. So what do we do when you do the supernode? Construct the supernode first. If you want to solve for circuits containing independent voltage sources also, so you construct the supernode. Next step, right? You write down KCL for the supernode, okay, and other nodes. So you get a set of equations, okay, and then you're going to write down the voltage constraints inside the supernode, right? Inside the supernode you would have some voltage constraints corresponding, having these voltage variables, right? And then now you can go ahead and solve the equations. Now suppose I take this guy. Let me get rid of some of these modifications. Okay. V1, V2, V3. Now actually, what would have happened if I had, let us say, if I had the voltage source here, like this. This is just a trivial case of the previous one, right? The earlier case I had the voltage source between nodes 1 and 2 or nodes 2 and 3 or whatever, between two independent nodes. Now I have the voltage source between the one particular node and the reference node. So what is the equation? What is the last equation? Would just be V2 equals Vx in this case, okay? The additional equation that you have would be V2 equal to Vx. Okay? One second. Okay, so let us go back to this guy that we have seen before several times. Okay, so we know what to do if we have, now we know how to solve resistors, current sources, independent voltage sources. What's left? What's left? Sorry? Dependent sources. Okay, anything else? Capacitors and inductors. So capacitors and inductors, we'll do it a little bit later because the equations are going to be going to involve what? Derivatives, right? We don't want to deal with those now. Okay, we'll still use the resistor as the passive element. Okay, in these kinds of structures. You will learn later on in the course how to deal with inductors and capacitors, but we'll do the case of the dependent sources. Okay. So, okay, which dependent source shall we do? We'll do a current source, that's easier. So let us say I had a controlled source Ix. Let us say we'll do a voltage controlled current source, okay, and so I'll define this voltage as Vx, okay, so this is some K times some Gm times Vx, right? Remember, if you want to multiply a voltage with something to get a current, that will look like a conductance, okay, that's why I've used the variable G, so I'll call it Gm here, okay, so this will be some Gm times Vx, and what is Vx? I have defined it as the voltage across R33, okay. In this particular case, it also happens to be R3, the voltage across R33 also happens to be V3, so I could have just called it Gm times V3. What do you do in this case? So we are considering the case with voltage controlled current sources. So what do you do in this case? What happens if you try to write KCL at node 1? Let's write it down. So that will give us the equation V1 G11 times V1, okay, plus Gm times V3, okay, equals IA, right? What will happen to at node 2? I'll have G22 times V2 plus maybe I'll just write it as G22 plus G23 times V2 minus G23 times V3, okay. What do you also have? Minus Gm times V3, correct? Should be equal to 0, right? And I can also combine these guys together. Correct? So at node 2, if I wrote the KCL, sum of all currents leaving the node, okay, I have V2 by V2 times G22, V2 minus V3 times G23, okay, so that takes care of these terms. So that takes care of this term and this term, okay. And then you also have a current entering the node, which is GMVX or GMV3, and that will give rise to the last term, Gm times V3, should be equal to sum of all independent currents entering the node, which is 0 in this case, okay. So what happens to your equations? So let us write down the third one also, and then we'll write down the matrix. What happens at N3? It stays the same as before, okay. I have minus G23 times V2 plus V3 this is the KCL at node 3, okay. So I have one current here, another current here, and that's equal to this guy. Okay, so now if I put it in matrix form, so I have G11, okay. What is the row 1 column 2? 0. What is row 1 column 3? GM. So I'll write down these because it's easier to write down. What is row 2 column 1? Row 2 column 1 is 0. Row 2 column 2 is G22 plus G23. What is row 2 column 3 is G23 plus minus G23 plus GM. Correct. What is the row 3 column 1? 0 minus G23. Okay. So now you still have a conductance matrix, except instead of just G11, G12, G23 and so on, you also have these extra terms cropping up corresponding to GM, right? How do you figure out what GM to put here? Where does this what signs, and how do you figure out the signs and the values? GM is the proportionality constant of the voltage controlled current source. Okay, and you find that of course the controlling variable is V3. Okay, so you will find this GM term entering in the third column, correct? Because it should multiply only the V3 term when you write the KCL. What else? What else do you notice? Because the current, so voltage controlled current source is connected between nodes 1 and 2, it will appear only in row 1 and row 2, correct? And it is leaving row 1 and entering row 2, so you all also know the directions, right? Any questions? Okay, so voltage control current sources are also straightforward, right? You can include those in your set of equations that you have learned so far. What about current control current sources? Okay, well, let's come to that. Let's take the other case. Suppose I have a voltage controlled voltage source. So I'll take the okay, so let us say, yeah, I'll take the same thing. This was K times Vx. The value of the voltage controlled voltage source was K times Vx, where Vx is the voltage across R23, which is V3. What will you do in this case? So again, you don't know the current passing through this control source. It could be anything, right? So you can construct a super node combining N1 and N2. So you can construct a super node, okay, combining N1 and N2. Okay, you can write down the KCL equations for N1 and N2, correct? Put together. So that will give you one equation. You have lost an equation, so you need to add another equation. What is that equation? So if you had to write, so the additional equation for this system, so you would go through the same procedure as you did for the independent voltage source. Okay, you construct the super node, write down KCL for the super node. The additional equation, the construction of the additional equation will change slightly. Okay, What did you do in the original case? Let's go back. We wrote down the voltage constraint between nodes 1 and 2, or between the nodes. We wrote down the voltage constraint between the nodes across which the independent voltage source was connected. Okay, we can do the same thing for the voltage controlled voltage source also. So the additional equation would be V2 minus V1 is K times Vx. Okay, so I'll rewrite this as minus V1 plus V2 minus K times V3 is 0. Okay, again you have to rearrange it in terms of the similar to the original equation that you had. You need some linear combination of the voltage variables on the left hand side. You need to have the independent constants on the right hand side. In this particular case, this is the equation describing the voltage constraint. Okay, of course the assumption is that you know what this K value is. Okay, so this would be the additional equation that you would concatenate to your original set of to your original conductance matrix, okay, and use to solve the system, right? This is also pretty straightforward. Any questions? Any questions? Okay, very good. So this is the additional equation you would use for the voltage controlled voltage source. What if you had a voltage controlled current? Sorry, we already did this. So what if you had a voltage current controlled voltage source? So that would be some Rx times Ix. Okay. The value of the voltage source depends on some current, and that current can be current through any element. So I'll change it slightly. I'll say this is Ix. Okay, I'll say Ix is the current through R23. So the value of that current controlled voltage source depends on the current through R23. Okay, so how will you set up the system of equations? Can you still construct a supernode? You can. Okay, so anytime you have either an independent voltage source or a dependent voltage source, you would go ahead and form the supernode. Okay, you would combine the terminals across which the voltage sources are connected and form the supernode and write down the equations. Okay, next step is to write down the voltage constraints, okay, for these supernodes, inside these supernodes. In this simple case we only have one. So what is the additional equation? If you had to write down the additional equation, so that would have the voltage constraints between nodes 1 and 2. So V2 minus V1 is some Rx times Ix. This is the original constraint. How do you write this? How do you get the additional equation in terms of what we expect to solve? Yes, so Ix is the current through some element. Okay, in this particular case it's a resistive element. You use the elemental relationship to represent it in terms of the voltages, right? So this is the same as Rx times, what is Ix? V2 minus V3 by R23. Okay, what do you do next? You rearrange the equation. Okay, so let me get some additional space here. So the equation I would have is minus V1, okay, plus 1 plus Rx by R23 times V2, okay, plus zero. Sorry? Oh yeah, of course. Thank you. 1 minus Rx by R23 plus Rx times V2 plus Rx by R23 times V3 is 0. So this is what you would concatenate with the conductance matrix. Okay. This is again a linear combination of V1, V2, V3. On the right hand side you will have 0. Okay. Any questions? Pretty straightforward, right? Once you know the basic concept, it's pretty straightforward. You can go ahead and keep constructing these kinds of additional equations, you know, for every set of voltage sources that you have. Okay, for every voltage source that you have, whether it's independent or dependent, okay, you can construct these constraints and then solve it using matrix inversion. Okay, so what we'll do is we'll stop here. In tomorrow's class, we'll do the last case, which is the current control current source. Okay, and then move on to the next set of things.